Okay, so in this video, we're going to discuss how to find eigenvalues and eigenvectors geometrically. So you get a feeling for what we're actually trying to compute or determine. So let's go ahead and find the eigenvalues and eigenvectors of this particular matrix. Now notice this time I'm not giving you one or the other, so it's a little more difficult now to figure out what the eigenvalues would be to find the corresponding eigenvectors, or to find an eigenvector to find the corresponding eigenvalues. So to do so, notice though that you can think of this process as a kind of a linear transformation, because you're taking a matrix and you're multiplying to a vector and you want to get a particular vector out. So that is a kind of mapping. So you can think of it as a linear transformation defined by matrix multiplication, where you're just taking the standard matrix A to define that matrix multiplication. So notice that this matrix then, 1, 0, 0, -1, that actually corresponds to just reflecting a vector in the x-axis. Because if you take the vector x, y and do the mapping, you get the vector x -y, and that's exactly what it does. It reflects the vector directly in the x-axis. So we'll use that fact in order to help us to figure out what the eigenvalues and eigenvectors would be by thinking of it in terms of just mapping lots of vectors. All we need to know now is what do we aim for? What are we looking for when we're looking at this mapping? Well, but we also notice though that if you take this linear transformation and apply it to the vector x, if it is an eigenvector, then the result has to be lambda x, because the transformation applied to x is the same as a times x, which is equivalent to lambda times x. So the important thing is, notice then that if t of x and x are multiples because of the lambda, that means they're parallel. So we're looking for vectors under this mapping so that we get the vector x and what it maps to are actually parallel vectors. So I'm going to show you how to go about doing that by looking at an animation. So if you look at this particular animation, all I'm going to do is move this vector around. What you see is the reflection transformation. It's reflecting the vector red to the vector green by just reflecting the red vector in the x-axis. So I'm trying to find a vector, the red vector, so that the green vector, the image, so those vectors are parallel. Clearly then this, what I have right here, that's not an eigenvalue, an eigenvector, because the two vectors are not parallel. But right here, they are. In fact, they're the same vector. That's okay. That would mean that a times x would equal x. So then what you see right here, the vector 0, 4, oh, sorry, no, 4, 0, the vector 4, 0 appears to be an eigenvector, and its eigenvalue would be 1, because the matrix times the vector 4, 0 gives you 1 times 4, 0. So then that looks like that the eigenvalue of 1, that the value of 1 is an eigenvalue, and 4, 0 is an eigenvector. But we know though that if 1 is an eigenvalue, then there's an eigenspace of vectors. So there's not just one eigenvector. In fact, any multiple of this vector would also be an eigenvector corresponding to the eigenvalue of 1, because it's a subspace. Any multiple of this vector would then be back in that same space. So notice, see, these are all eigenvectors, all of them. They're all corresponding to the same eigenvalue. Look at the vector 2, 0. If you take the vector 2, 0 and multiply it to the matrix, or multiply it by the matrix, you get back the red vector, which is the vector 2, 0. So a times x equals x, and the eigenvalue here is 1. So there's more though. There's other eigenvectors out there. It actually is right here. See, those two vectors are actually, in this case, parallel to each other because of multiples. The vector 2, 0, oh no, sorry, the vector 0, 2. The vector 0, 2, that's the red one, gets mapped to the vector 0, -2. So that's the opposite of the original vector. So if I would write down a times x equals -x in this case. So 0, 2 is an eigenvector, but this time the eigenvalue is -1, -1. Now for the eigenvalue of -1, there's an eigenspace, which means that any vector that's an eigenvector corresponding to -1, I can do any multiple of it, and it would also be an eigenvector. In particular, notice right here, see that vector? 0, 4, that is also an eigenvector for the eigenvalue -1, because those two vectors are in the same subspace. It's kind of neat, right? All these vectors here, all these vectors along here, these are all eigenvectors for the eigenvalue -1. Others, though, you can see they're not. Now, we need kind of a way to do this quickly, because you can't do this animation every time. That'd be crazy. So another way to do the same thing is with a picture, and to generate the picture to show you kind of how it's done. Instead of having the eigenvector starting in standard position, we put the tail of the mapping, the tail of the image of the vector, at the end of the vector we're using as input. So the purple vector here is the image vector of A times X. The red vector is X. If the red vector is an eigenvector, then they would point in the same direction, see? So it's easy then. See, these two vectors here don't point in the same direction, or at least they're not parallel to each other. See, they're not parallel to each other. So these things here, all these red vectors, these are not eigenvectors, none of them. But that guy right there is, because they are parallel. The image vector and the original vector are parallel to each other. Now, if you look at this vector, they're not pointing in the same direction, but they certainly are parallel to each other. See, because they're at least on the same line going through the origin. So yeah, so then that vector is an eigenvector. So is this one. So is that one. So all of these also are all eigenvectors. That makes it really easy to go and find eigenvectors by using this little trick. Now you can use this in a picture really quickly. What you do is that you look at a unit circle. On the unit circle, that will then generate for you a whole lot of vectors. They're usually in blue. And at the end of each of those vectors, you take the image and put the tail end of the image vector on the head or the terminal end of your input vector. And if the vectors are ever in the same direction, or at least in the same line to the origin, you have just found an eigenvector. So to show you what I mean, I'll give you a couple quick pictures to give you examples. So here's one example. The matrix here is 1/4, 7, 1, 3, 5. The blue vectors are the input vectors. They're all unit vectors. The length of the vector doesn't matter, because once you have an eigenvector, any multiple of it will still be an eigenvector for the exact same eigenvalue, because eigenvectors belong to subspaces. So then any multiple of it will be back in the same space. So the blue vectors are the input vectors. The red vectors are the outputs. And I put the outputs so that their tails are at the heads of the inputs. We're looking for vectors then are in the same kind of direction. So notice that you can see one right around here, right here. That vector appears to be so that its image is in the same direction as the input. So then that right there, that vector, which appears to be maybe like 1, 1, or at least in that direction, that vector appears to be an eigenvector. And you can tell by looking at the vector. Here is the input. And then I'll try to draw another one for you. And then over here, this guy over here, that's the corresponding output. Notice that this is the length of 1, but this appears to be a length 2. So I would guess that the eigenvector is maybe 1, 1, and the eigenvalue for that eigenvector would be 2. I'm guessing. You can see another one right here. This appears right here to be an eigenvector, because notice the output vector, when put tail ahead with the input, they're kind of in the same direction. They're parallel to each other. And here, that vector, I don't know what that vector would be. If I were to keep in that direction, maybe it's -1, 3. If I were to keep going out here, just imagine I keep going out this way, might be -1, 3. And I'd guess that since this length appears to be 1, and this appears to be the same length, I say the eigenvalue is 1. I don't know, but at least it gives us an idea of what the eigenvalues should be and kind of what they do for us. What we need to do is to have some kind of process, some algebraic process to crack into either finding the eigenvectors first or to find the eigenvalues first. Once we have one, we can get the other. Once we get one, we can easily get the other. So we have to be careful, because if you look at this one example, notice that the input vectors, the guys in blue, and the output vectors for each of those blue vectors, none of them are in this, they're not, some of them are in the same straight line. it appears to this matrix that there are no eigenvectors. And that's actually not true. There are eigenvectors. The problem is that they're complex, which means you can't see them in the picture because this is only real numbers. It's in a real plane. So there are eigenvectors. They're just complex. And the eigenvalues, unfortunately, are also complex. So this technique I just gave you to try to visualize what the eigenvalues and eigenvectors are, it doesn't actually always work. So what we need is some quick, hard, fast method. How can we go about finding either the eigenvalues first or the eigenvectors first? Well, that's actually really easy because of some of the work we've already done, at least for 2x2s. If you give me a 2x2 matrix, if we know that lambda is an eigenvalue, that means then A minus lambda times I has a non-trivial null space. But we then know that that matrix is not invertible because of the fundamental theorem of invertible matrices. But if a 2x2 matrix, and that's what A minus lambda times I would be, if a 2x2 matrix does not have an inverse, then we remember its determinant is 0. I actually went through a long proof just to get that established. So we know the determinant is not 0. And that actually gives us an equation because this side would be in lambda only. It's all numbers in lambda. And this would be a number also. That would be a polynomial equation in lambda that any single eigenvalue would have to satisfy. So I want to know then for this matrix you see 1, 2, 5, 4, what are the eigenvalues? Once we know the eigenvalues, we can find a basis for the eigenspaces to get a bunch of eigenvectors, one or many more than that for every eigenvalue. Well, if this thing is going to have eigenvalues, that means that if I take the determinant of A minus lambda times I, that's got to be 0. So then let's see what A minus lambda times I looks like. You have A minus, so the matrix A is 1, 2, 5, 4. I'll subtract lambda times the matrix I, which here is 1, 0, 0, 1. That matrix would then be 1 minus lambda, a 2, a 5, and a 4 minus lambda. But if you remember, though, that we proved that the determinant is formed by taking a particular multiplication. So the determinant here of A minus lambda times I, that is a product of 1 minus lambda times 4 minus lambda minus 2 times 5. Remember, you take these, you guys, and multiply them. That was the A and the B. Multiply those. You then take the 5 and the 2 and multiply those together, and then you subtract the product. So this would then be just multiplying it out. That would then give you a lambda squared. You then have minus 5 lambda. You then have plus a 4 and minus 10. That is lambda squared minus 5 times lambda minus 6 equals 0, because the determinant here has to equal 0 if lambda is an eigenvalue. That means then if you look at the equation, that implies that lambda minus 6 times lambda plus 1 is 0. And the only such eigen number solutions would be lambda equals 6 and lambda equals -1. So then if there is an eigenvalue, it's either 6 or -1. And by reversing this process, because it's all these are equivalent statements, if lambda is 6 or lambda is -1, you will get an eigenvalue. In other words, A minus that eigenvalue times I will have a non-trivial null space. There is a non-trivial eigenspace for that eigenvalue. Once we have the eigenvalues, you can then use the process you learned earlier on in these videos to find the basis for each eigenspace. And I believe that's it for now. What we need to do then is to take what I've just shown you and to extend these ideas. The only thing we need to extend actually is this result. Everything else I did today did not depend upon the size of the matrix. This one does, because I showed you a way to give you a mapping to assign to every matrix a number, so that if that number is 0, then the matrix does not have an inverse. And if that number is non-zero, then it did have an inverse. We need to take the idea of a determinant and to generalize it to more than just 2 by 2 matrices. And I believe that's enough for now.